So 2.4, one-sided limits, is pretty much a summary of what we've done with limits so far for one-sided. But there are a few new things they add in here that I want to talk about. And first, let's just take a look at a graph again and how to get limits by looking at a graph. So this is from your book, and we'll just check this one out. So A, we're going to so here's our function. We're going to approach -1 from the right. And is it true or false that this equals 1? So here's -1. We're going to approach it from the right. So that means we're going to walk along the function. And as we get closer and closer to the input, what height are we at? We're at a height of 1. So yes, it's true. Approaching -1 from the right has a limit of 1. So let's check out B. Now B is actually a two-sided limit because we can see the 2 here has no superscript. There's no plus or minus there. So we have to check out the left and right limit for B. And so at 2. So if we approach 2 from the left, as we get closer and closer to 2, we're at a height of 2. And same if we approach from the right. If we approach from the right, as we get closer and closer to 2, we're at a height of 2. Now, what's the deal with this dot up here? Well, that's a jump. That we go here, and if we actually go to 2, we would jump up to here, and we jump back down. But remember, as we approach means we never actually become 2. So the limit never jumps to this point. And so this limit does exist on both sides. Both sides it equals 1, actually is the height there. And actually, so this statement is false. It says the limit does not exist. That's false. The limit does exist at 2. The limit always exists at holes. So let's check out C. We want to know, again, a two-sided limit. As we approach 2, is this limit 2? Well, we just talked about that. This limit is actually 1. 2 is where this point is, and then the limit never just jumps to that point. So is that limit 2? No. The limit is 1, and so that is false. Let's check out D. We want to approach 1 from the left. So here's 1. We'll approach it from the left, so we'll follow the function along. As we get closer and closer to our input, we find we're at a height of 2. So this limit is 2, and that's what it's saying. As we approach 1 from the left, is this limit 2? Yes, it is, and that is true. Let's check out E. Approaching 1 from the right. What is that? Well, here's 1. Approach it from the right. So we'll walk along the function. As we get closer and closer to our input, we find we're at a height of 1. And so, yes, the right limit there is 1, and that is also true. So let's check out F. Now they're asking, does the two-sided limit at 1, it's saying it does not exist. And so that means the left, here's the left, and the right, if these equal, then the limit exists. They don't equal, this is 2 and this is 1, so the limit does not exist, and so F is a true statement. How about G? G is asking, at 0, does the right-sided limit, approaching from the right, equal approaching from the left? And so if we look at 0, If we approach from the left, we'll be at height of 0. And if we approach from the right, we will also be at a height of 0. And so these two limits do equal. And so that's true. How about h? H is asking for a two-sided limit. Does this limit exist at every point in the open interval -1 to 1? So here's -1 to 1. And remember, the two-sided limit and the one-sided limit always exist on a solid connected line. So from -1 to 1, we are on a solid connected line. So yes, the limit exists everywhere in this open interval. And so h is true. Now they do have to say open interval here. You can't say closed interval, because if you have a closed interval, then you can't approach from the left. And J actually gets to that, so we'll do that one in a moment. But let's check out I. I wants to know if the limit exists everywhere in the open interval 1 to 3. So here's 1, here's 3. In this open interval, does it exist everywhere? And it does. Now this is a broken line, so we have two lines here. We have a line here, and then a line here that the limit will always be on. The only questionable spot is at 2, but we did that limit already. The limit of a whole always exists, and so the limit does exist everywhere from 1 to 3. And again, the limit always exists at a whole. So I is true. Now here's a tricky one. J, we want to approach -1 from the left, is what it's saying. Now -1, notice that there's nothing to the left. There's nothing here. And we have to acknowledge that there's nothing there. You can't just make anything up. So there's nothing to the left, which means we can't approach -1. We have no idea how to approach because there's nothing there. And so there's no way a limit can exist when we can't approach that number. And so J is false. Is this limit 0? No, this limit doesn't exist because we have no way to approach it. And that goes back to why these statements say open interval. Because it's a closed interval, that means there's nothing to the left of it. And if there's nothing to the left of it, then we can't approach from the left. And then finally K here, 3 from the right. So here's 3. There's nothing to the right. And so we acknowledge there's nothing here. We don't make anything up. And so there's no way to approach 3 from the right. There's no way to do that. We have no idea. There's nothing here. And so that limit doesn't exist. And that's what they're saying. And so K is true. So let's check out a couple other problems here. And here's another problem from the book, this limit here. And so they're asking for a one-sided limit, approaching -half from the left. And now remember, the simple thing to do here is just plug the number in. If that works, then it works. And again, that the only thing you have to be careful there is that you're not at a gap. We aren't at a gap here though. So we can just plug our number in is the simple thing to do. And if that works, then that works. And we'll see what that equals. So 2 minus 0.5. And my math app is certainly not going to like those decimals there. And so what we can do is multiply both of the numerator and denominator by 10. And then we can see that simplifies. 15 divided by 5 is 3. And there's our answer. If we're not at a gap, then we can just plug the number in. And if we get an answer out, that's our answer. So the book will still throw ones like this at you where you don't have to do anything. Just the number works. So let's try another one. So from recall from 2.2 that we deal with the square root by using the conjugate. And so we'll have to multiply this by the conjugate. And so there's our expression. And we're definitely going to want to clean that up. So in the numerator, I'm just going to look over here to see it. Get rid of all this stuff. We're going to multiply that numerator together. So square root times the square root will get us just what's under the square root. And then square root times the plus square root of 5 and the square root times the minus square root of 5, those will subtract out. That always happens with the conjugate, that those middle terms will subtract out. And so then all we have left is minus square root of 5 times positive square root of 5 to get us a minus 5. And then we'll do some more cleaning up on that, just trying to leave some steps here. And of those 5s will subtract out. And we can have an h divide out here. And I can just stick this over here. Clean that all up. And there's our limit. And again, all I did there was stuff from 2.2. We found we were in the indeterminate form, and then we got out of that by using the conjugate. So if we look at this now, if we plug in 0, we're no longer in the indeterminate form. And that's our answer. So if we just plug in 0, and figure out what that is, and square root of 5 plus square root of 5 is 2 square root of 5. And then those 2's cancel to get us our final answer. So let's check out another one. And this one's got an absolute value in it. And hopefully you recall some stuff from that absolute value video, because we're going to use it here. How do we deal with this absolute value? Well, let's look at our input. X is going to minus 2 from the left. So that means we're going to be dealing with numbers like minus 2.1, minus 2.01. We're approaching minus 2 from the left. And if we plug these numbers into the absolute value, then notice this will always be negative. So minus 2.1 plus 2 will be a minus 0.1. So as we approach minus 2 from the left, x plus 2 is always negative. And recall how we deal with an absolute value if we know it's always negative inside. So we know x is less than 2. And so the absolute value, what's inside, is always negative. And so we can get rid of the absolute value then by multiplying all of that then by a minus sign. Because we know x is less than 2. Oops, I should actually say minus 2 here. Because we know it's less than minus 2. Minus 2, x plus 2 will always be negative. And so we can get rid of the absolute value sign by replacing it with a minus sign. And now we can simplify this because these x plus 2's will cancel. And this minus sign is a constant. It means minus 1. And we can pull that outside the limit. And these x plus 2's divide out. And now notice, if we plug the number in, it works. And then that's going to be our answer. So if we just plug the number in, x is minus 2 plus 3. And 3 minus 2 is 1 times the minus gives us our final answer. So this limit with the absolute value approaching from the left, minus 1. And again, I wanted to point this problem out again to show you how these absolute value properties that I talked about in that previous video are things that you will see more of. And that is 2.4. It is basically 2.2, but with an emphasis on one-sided limits. And notice we did all the same strategies that we did in 2.2. And then we did use this new thing with the absolute value, breaking that down to help us with this problem. And that's 2.4.